What is up, most distinguished patrons of this channel? Today I'm going to teach you how to do something you probably shouldn't do, and that's how to weld on spring steel. So with that said, let's get into it. So this video I'm putting out there with a solid disclaimer. I would not recommend anyone, that includes you watching this, attempting this on something other than an absolute emergency repair. The reasons are simple. Well, for one, if you go and weld a leaf spring in your state, you're probably in violation of the state law, especially under the commercial vehicle code, so that's not too wise. And second, this is one of those things that there's a lot of liability in, and it's probably not too smart to do anything as far as a repair on something like a leaf spring. Now, that is exactly what I have in front of us today. This is a piece of a leaf spring. And for those of you who don't know, leaf springs are made out of what is known as spring steel, and they have very particular properties that make it work great as a spring, aka you have a lot of deflection and you can bend it and it returns back to its original shape, and it doesn't have memory for the most part, and it works great for its intended purposes. The problem is that welding this stuff creates a lot of changes to the metal itself and in a heat affected zone that makes this stuff arguably unweldable. Now, I've made a career of fixing stuff that is unfixable and welding stuff that a lot of people can't, such as aluminum and stainless steel. But spring steel is one of those things that if somebody ever came to me with a broken leaf spring like this and told me to fix it, I would tell them to disappear, and I'm not doing that. But I have done this in an emergency. I do a lot of off-roading of vehicles, and more than once I found myself where I or somebody else broke a spring. And guess what? To get something off the trail, it's either you tow it for 4 or 5 hours through about the harshest terrain you can imagine, or you can do a trailside repair on it. So what I'm about to show you is more or less something that you might be able to use in an emergency to get something with a broken spring out of a bad situation. Under no circumstances should you take that vehicle or whatever it is and just start driving down the highway and think everything's fine. Now, with that said, let's talk a little bit about this material. I recently did a video, link in the description to that, where I welded AR500 plate, and we found out that AR500 plate isn't that difficult to weld. It welds like mild steel. You just typically need to preheat it and watch how fast it cools, and everything is fine. This material does not fall under that category at all. This material here is not fine after you weld it together. And what you have to understand is that when you take this and weld it to itself, you produce an alloy of both the base material and your filler material, and that alloy is going to be extremely hard, extremely brittle. What you need to understand with this material is when it comes out of the machine that more or less shapes it in this manner, especially on this case where it's thick and a middle thin on the ends, this material does not perform the way it does when you see it in a leaf spring, or even for that matter a coil spring. Only after heat treatment does this material function the way that it does as a spring. So the heat treatment is absolutely critical. And unlike AR500, which is basically just designed to be very abrasion resistant and very hard, this stuff is designed to function like a spring. Therefore, the heat treatment of this is absolutely critical. And what you're going to find if you go and try and just weld this stuff, and it doesn't matter if you use 312 stainless, nickel, or 7018 or ER70, the completed weld with this junk will be so brittle that it will just fail almost immediately. Therefore, to have any success in welding this stuff, you need to be very critical with your post-heating, your preheating, as well as what filler materials you're using. Now, in my experience, you can actually weld this stuff with ER70 or 7018. However, you will probably have more success with 312 stainless, in my opinion. So what I'm going to do some demonstrations is I'm going to cut this leaf spring into sections, and then we're just going to weld it together do everything wrong at first, then we're going to come back, do things right, and we're going to look at the stark difference. Well, I managed to cut this with my bandsaw, and I'll tell you, it's not too happy about cutting this stuff. It's pretty hard on the teeth on a bandsaw blade. Anyways, some casualties are expected when working with this stuff. So the deal is, I'm going to weld both this piece and this piece to this thicker piece right here. This is the same thickness as this. To be fair, this part is roughly the same thickness. For all practical purposes, it won't matter. I will preheat all of the pieces to 300 degrees before I weld them. However, this one, I am not going to do the secret sauce that I know generally works with this stuff to get it to work, aka a weld hold. I'm just going to weld it, and then we're going to put it in the vise over there and hit it with a hammer when it's cooled down and see what happens. After we have a pass or a failure with that, we are going to go and weld this one, same deal, 7018. But I'm going to do my little secret sauce special process to make this possibly work, and then we're going to repeat the test and hit it with a hammer and see what happens, and hopefully learn something along the way. So let me go get my torch and preheat this up to 300 and start welding. So this is all cooled off, as you can see, and our weld is successful in quotations. I don't see any visible cracking on the toe line or the center of the weld. So by all practical purposes, this is welded, right? And it should be fine. Well, that's where visual inspection is a bit misleading on this. And to prove that, let's go chuck this in the vise and hit it with a hammer. All right, I got it chucked up in the vise here. I'm going to hit it with a hammer and we're going to see what happens. Well, look at that. As brittle can be. That's not good. So it failed right at the toe line of the weld, right between the interface of the weld itself and the material. And this is exactly what I would expect to find. Now, I didn't really take that big of a swing and it pretty much failed immediately. And that is why if you were to just weld a leaf spring on a vehicle or even a coil spring, although that would be a lot harder, but a leaf spring on a vehicle is going to fail almost immediately because as it flexes, would impart probably as much force as that hammer blow and it would just break. Now, I know a lot of you are probably shouting at the camera now, well, 312 stainless would have solved this. And the answer is no, actually it wouldn't have. 312 stainless rods and fillers or some kind of nickel-based alloy or some wonder rod would generally produce a less brittle weld, but this is as much a material failure as it is the weld material failure, so base material failure. And the solution to this problem actually is not just going to 312 stainless or some nickel alloy. The truth to this is we have to do a form of heat treatment. Now, I'm going to be honest with you guys. Heat treatment and at home don't really go together because there's a huge science to that. How hot you get something, how thoroughly heated something is all the way through, end to end. Like in the case of this leaf spring, we have differing thicknesses. Like this is something that's really hard to heat treat, not to mention how fast you cool it after it is brought up to temperature, how many cycles you do. All these things play a massive role into producing spring steel that functions as spring steel. So that's why I'm going to show you what I have done in the past for emergency repairs, and that is what I call the backwoods heat treatment. So there's two ways that we can deal with this problem that we're faced with the base material. One is to preheat the material to about 1,000 degrees, then weld it. Odds are that that would provide a solution. However, in my experience, when I've done that, I seem to have more failures with the base material, just like you saw in this, than what I'm going to show you. Normally, I would do this type of repair with a 312 stainless-based rod. And just like you saw in this 7018, the weld isn't cracked by any means, and the weld isn't what failed. More or less, that base material had more to do with the failure. And that's why what we're going to do is we're going to take this piece and we're going to weld it onto there. We're going to preheat everything to 300 degrees just the same. I'm going to let it air cool just like I did for this guy, didn't quench it or anything. And then we're going to heat it up to a dull red color and we're going to let it air cool. Now, a lot of people, when trying to heat treat or temper this stuff, will heat it up to that dull red color and then quench it in oil. To me, as an emergency repair, you probably don't have much oil laying around, nor is it probably that smart. And I know that heating it to dull red and letting it air cool will get a leaf spring to get you off a trail or out of an emergency situation. So my opinion is I would not go and screw around with oil, because if the oil is super cold for some reason, like it's in the back of your vehicle, is cold outside, and you go and dip that steel, you can have a drastic effect on it, more so than you would think. So once again, we have made it through the welding process, and I don't see any evidence of cracks or weld failures or anything like that. So that is a great sign. But once again, this is identical to what we just tested that broke, and we don't want this to break, because if it breaks, well, it's of no use to us, right? So what we're going to do is I'm going to take that torch, put a lot of heat into this, and get it to a dull red. Now, dull red is basically a faint red where you can barely see it in dim light. So you don't want this. If you can see it like cherry red or white or any of that, you've heated it far too hot and now you're in trouble. So we're going to be looking for a dull red. We want to see this base material, this upright plate, along with this weld, all roughly the same color. Do not do this fast. If you just sit and pump a lot of heat in one area, by time you get other areas up to temp, you're probably going to overheat the area you initially started with. So you want to take it slow. You want the whole material here and here, preferably dull red all the way through it. You don't want to see, especially if it's a thicker spring piece where it's just red on the surface and there's nothing even remotely as hot on the back side. So the whole area needs to be dull red. So anyways, while this junk is cooling off, let's talk a little bit about some more details. When it comes to cooling this, you want to heat it up to that dull red and just let it air cool over time. It might take 30 minutes or so before you could even handle it, and that's perfectly okay. Like I said earlier, a lot of guys like to quench this in oil. I just don't find that that's too effective on the side of a trail, because now you got a bucket of oil that you don't want to be carrying around. And if the oil's cold or any number of things, you could run into issues where you're going to change the results. I know that this is going to work fairly effectively, so I wouldn't recommend oil. Now, as far as consumables go, this is a job if you're stick welding for 7018 or 312 stainless or some other kind of alloy that's similar to 312. My recommendation is to take it out of a brand new pack. Now with 7018, it's only low hydrogen if it comes out of a brand new pack or a rod oven. It's in your best interest to keep rods properly stored in your garage or in your trail rig or whatever if you're going to be doing a repair like this, because if the rod absorbs moisture, in the case of 7018, that moisture will get into the weld pool and will create what's called hydrogen embrittlement. This material is highly susceptible to hydrogen embrittlement, and that will cause failures as well because it's going to lose its ductility. As far as ER70 with TIG and MIG, generally speaking, you're going to be just fine with that. However, I would not weld this junk with 100% CO2. That will typically make a much harder weld on this material, and it'll be far more prone to failure, even in the sake of a simple repair just to get you from point A to point B, and that's it. So do not use 100% CO2 on this. Going back to what I was saying about the low hydrogen, 312 stainless and many of those wonder rods that are out there oftentimes are not properly stored. Generally speaking, 312 and most stainless rods should be stored in a rod oven or taken out of a brand new sealed pack. So even with those rods, you should be smart about it and keep a sealed pack around and use them for repair like this on an as-needed basis. And once again, do not use them if they've been out sitting, absorbing moisture for a while, because again, it can lead to hydrogen embrittlement. Well, this thing's been sitting for a good 10 minutes already, and it's still at 400 degrees almost. So that's a good sign. You don't want this junk to cool fast. All right, well, I'm just going to let it air cool, and we'll come back, chuck it in a vise, and hit it with a hammer and see what happens. So I chipped the slag off of this and everything looks really good. This weld is pretty much defect free. As you can see, it has cooled down a lot. It took a long time for this to cool because of how thick this was and how hot the preheat was. But for all practical purposes, we're in the same boat we were before. The only difference is that we did a backyard, backwoods heat treatment on it. So let me zoom out and let's hit this with a hammer and see what we got. Well, it's not going to break, as you can see. I need to learn to swing a hammer, Jesus. So as you can see, we were able to get this to where it didn't outright fail just like it did in the first test. So that is a huge improvement. In my actual hands-on experience doing this and repairing stuff for on-trail leaf spring failures, I have not had one fail after welding it. Arguably, this should have been welded with 312 stainless or some kind of alloy similar to that, simply because the carbon that would be absorbed from the base material wouldn't make the weld overly hard. But as you can see, even normal 7018 is perfectly okay to weld this stuff and get a reasonable result. Now, will this be exactly the same as a unrepaired leaf spring? Absolutely not. That's why anytime I found myself doing a repair like this, I end up ordering a new leaf spring, installing it, and just using the other one for scrap metal or whatever. Because let's face it, this in the long run is not a permanent fix. It very well might hold up, but you will change the overall heat treatment of the leaf spring to where it's inconsistent, and more than likely over time it's going to break somewhere else on the spring, not where you repaired it. So those are all things to consider. But for all practical purposes, this could be a lifesaver for you to rescue something that's broken, and that's why I'm sharing this with you. Now, with that said, I got to put this disclaimer out there once again, because you know lawyers. No, you shouldn't do this and put it on the highway. And if the state patrol ever finds welds on a leaf spring on a truck, good luck, buddy. You're going to be sitting in jail, not me. Anyways, hopefully you learned something. Hopefully you found a new skill today. And if you have any comments or questions or thoughts on this, feel free to leave them. Until next time.